Hey everyone, hope that you're having a great day. Today we're going to talk about limits, which is what all of calculus is based on, and also is just a great pre-calculus topic. It has to do with looking at functions and what happens as x values approach a certain number, what is happening to the y values. So we've talked a little bit about some limits, and that's where we're going to start. It's kind of what we've seen before. So what we've seen before is we've seen a lot of limits as x approaches a value, or as x approaches infinity, something like this, or limit as x approaches negative infinity. We've seen a lot of these, and we've been doing a lot with rational functions. So if you have like limit as x approaches infinity of, I don't know, like 3x squared minus 2x plus 1, and then on the bottom, let's say you had 7x to the fourth minus 2x. So what we've talked about is you should look at the degree. Right? If the degree is bigger on the top or on the bottom, or if they're the same. Here we have a bigger degree on the bottom, so this is equal to 0. Because the bottom is going to get very large, the top is going to get big, but not as big as the bottom, and so that equals 0. If they're the same, so if you're like 3x to the, I don't know, fifth minus 2x plus 1 over 2x to the fifth plus 5, this would just be the leading coefficients because we have the same degree, so it'd be 3/2. Because as x gets very large, the smaller degrees don't matter, and then the x to the fifths just cancel. And then if we had the limit as, sorry, we went to negative infinity here, still the same deal, because they're going to cancel out, it'll be 3/2. Limit as x approaches infinity of, let's say, like 2x squared over x, something like that. No, let's make it a form of fun, like x plus 1. Bigger degree on the top, this does not exist. You could say it diverges. Or you could say that in this case it would be positive infinity. Because we have a higher degree on top, so that's going to grow very big, and the bottom will not be able to keep up. So this is kind of what we've seen are these rational functions and the idea of just looking at the power of the top and the bottom, and that's all you have to look at. So now where we're going is looking at things where the x is approaching actually a number. So instead of approaching infinity or negative infinity, we're not looking at what we call the end behavior, right? So like a function like this has end behavior, whereas you go to negative infinity, it's going to 0, and positive infinity also going to 0. We might be approaching a value. So here it's as x approaches 2. So what this is saying is as the x values get very, very close to 2, what is happening to x squared? Well, if you think about that function, right, x squared is a parabola. As x gets very, very close to 2, if we think about actually what's happening to the y values, they should be getting close to 4. And I actually have a Desmos set up for this, so let's go out and take a look at that. I'm going to keep those, and let's go over to Desmos. So first one I want is actually this guy up here. So here's our function x squared, and I have a little slider here, and what I want to do is show that I'm just going to use my slider along the x-axis, and you see that as my x is at different values, the y increases at different rates. So when x gets further out, the y is growing faster and faster, and what I want to see is as x gets close to 2, what is happening to the function value? So as x gets close to 2 over here, this green line up here that's following along the y-axis is going to tell me what's happening to the function x squared. So if I slide it close to 2, we see that that green line is going to approach really close to 4. Do you see how as the x approaches 2, the y value approaches 4 from the left or from the right? From the right also, as x approaches 2, you see we're really close to 2. The y value is further away from 4, but as I get close to 2, right there, they're actually going to line up perfectly. Okay, now this makes sense because f of 2 is 4. Right? Now this is kind of an uninteresting example because all I have to do is say, well, 2 squared is 4, so when x gets really close to 2, the y is going to be really close to 4. And that's really just the answer to this one. So, make this bigger. As x approaches 2, all we do is just plug it into x squared. So 2 squared is equal to 4. And we're done. That is our limit. So the way you would write that is the limit as x approaches 2 of x squared is equal to 4. Because you just plug it in. That's all you have to do. Okay. The next one, very similar. If I plug 2 into this equation, if I plug 2 in on the top, I get 4 minus 6 minus 10. And on the bottom, I get negative 3. 4 minus 6 is negative 2, minus 10 is negative 12 over negative 3 is also 4. Didn't even plan that. So as 2 goes, as this function is approaching 2, the x values, the y values should approach 4. And let's take a look and see if that is the case. So go over to our Desmos again. I think I've got that ready to go right here. Okay. So here's our Desmos. So as x approaches 2, so we're getting close to 2 there, we see once again our y values are getting really close to 4. So both of these are not very exciting because they are what are called continuous functions at those points. So both our parabola and our, it looks like this is a line here, which is kind of weird. We'll talk about that a little bit later because it doesn't look like it should be a line. But as we approach, we actually are equal to the function value. So pretty boring limits. Over here also, as x approaches 2, y approaches 4, so not very exciting. So like I said, those are what are called continuous functions. So if f is a continuous function, if we have a function that's continuous, then we have these uninteresting limits, because as the x value approaches a number, it's just going to approach the function value. So the way that we talk about a continuous function is we say if, so, this is, I just wanted to make sure I define it the same way that it is on your packet. So it would say is the limit as x approaches c of f of x is equal to f of c if and only if f of x is continuous at x equals c. Okay. So let's break that down a little bit. That means that if the limit as x approaches a certain value is equal to the function value, it makes sense that would be continuous, because as x approaches a value, you would expect the y values to be getting closer to that value. Now there are some functions that do weird things, that have asymptotes like this. As x approaches 0 from either side, there is no function value at 0, so we're discontinuous at 0. So this is a really good calculus definition of continuity. So let's take a look at this last part here. So same function, but this time let's see what value we're asking for. So it looks like we're asking for the value of 5. If you plug in 5 on the top, you get 25 minus 15 minus 10, which is 0. And on the bottom, you also get 0. Well, that's an issue because we don't like dividing by 0. So what we have to do is we have to do a little bit more work and see if we can make this a little bit different. So first of all, let's take a look and see what's actually going on here. So let's go back to Desmos. Keep those. And it's right over here. So we're going to go back to our function. It looks like we have a hole there. So if we approach 5, what does it look like the y values are getting close to? Looks like they're getting close to 7, right? And from the other side as well, looks like they're getting close to 7 as I approach 5 with x. And if you actually go right to 5, let's see if Desmos is going to do it for me. See how it disappears there for just a second? Because it freaks out. It says, no, if you plug in 5 here, I get 0 over 0, so it doesn't actually give me a function value. But the thing about limits is limits are funny because they care about everything near the point. The only thing they don't care about at all is the actual point itself. So if there's a hole, even if it was filled in up here, like even if there's a dot up here somewhere, if there's a hole right there, the limit is just whatever value the y values are approaching as x gets close to that number. So functions are all about what's happening near this x value. So the closer I get to 5, the closer the y values get to 7. Even though it's undefined right at 5, it looks like that limit should be 7. Now how can we prove that algebraically? So what I'm going to do is I'm going to do a little bit more work and see if I can make this a little bit prettier. So I'm going to factor the top, x and x. Factoring skills, have to pull those out of the bag. Bottom we got x minus 5. So negative 10 and negative 3. Looks like we need a negative 5 and a plus 2. Hey, these cancel out. This now makes sense why we have a line. It's x plus 2 everywhere except at 5, because that would be dividing by 0. So we had that line that had the hole in it. X plus 2 looks something like this. And then there's going to be that little hole at 5, 7. But the limit, as you approach 5, those y values are getting closer to 7. Because if you plug 5 in now, hey, look at that. 5 plus 2 is 7. So let's take a look at some of the strategies we can use to actually find these limits. So the first strategy is just to plug in the number, and that worked for our first function right here, x squared. It also worked for our second one. Even though this function had a hole, when we plugged in 2, it gave us a number. So plug in the number. That's all you have to do. If it's defined and you get a number, then you're done. That would mean that it's continuous at that point. So I should add that at that point. So if your function value is defined, so as x approaches 2, we plug in 2, it works out just fine. Here we plug in 2, works out just fine. Then that means that we actually have a continuous function at that point. Doesn't always work out that nicely. So if you have 0 on the top and bottom, which is what happened over here, then you might have to try factoring. See if something cancels out. That's exactly what happened with this problem. If it does, it's a hole. So that's what happened on our last one. We just had to cancel out the x minus 5 after factoring, and then we end up with x plus 2 equals 7, and we're done. Now there's one more case that you're going to see on your homework where if you can't factor, but maybe there's a root, try multiplying by the conjugate. And we're going to look at an example like that in just a minute. So what I'm going to do now is I'm going to look through the 3 examples that are on the first sheet of your limit section of your packet, and we're going to talk through those, and then you should be able to do all of the limits that are in your packet. So first out, we'll start with an example that has a root in it. And this one actually, sorry, I had to go back and remember what this was because there's no conjugate here. But this one, we're just going to try plugging it in. Okay, so it'd be root 3 plus 1 over 3 squared minus 1. So that is the square root of 4 over 9 minus 1, which is 2 over 8. That's 1/4. So we got a number. So this was our first strategy. We plugged it in, gave us a number, we have our limit. If you were to graph this, I have no idea what this graph looks like, but as you get close to 3, if this is 1, you're going to be getting closer to 1/4. So just guessing what this looks like, I'm not really sure. Maybe it comes down like this at that point. So as you get close to 3, the y values get close to 1/4. Okay, and you just get that by plugging it in. So plugging it in is definitely the easiest strategy. Let's see what else we can do. So this guy, if we plug in 1 on the top, 1 plus 2 or 3 minus 3 is 0. Looking suspicious. On the bottom, we also get 0. So this guy, let's see if we can factor it. So we'll have the limit as x approaches 1. On the top, looks like we have x and x. 3 I can only get with a 3 and a 1. And we need one of them to be positive. Looks like plus 3 minus 1 will get us to positive 2. And then on the bottom, x squared minus 1 is x plus 1. X minus 1. The x minus 1's cancel. Nice. So now when I plug in 1, I won't get that 0 over 0. So when I plug in 1 now, I'll get 4 on the top, 2 on the bottom. Looks like that is 2. So this would be a hole. If you were to graph this, you would have a hole at 1, 2. Maybe a hole like that. And then, let's see, this guy has asymptotes at negative 1, because positive 1's just a hole. So this is back to our rational function graphing. Oh boy. And it looks like we have a 0 at 3. So my bet is that this comes down like this. And then as we go to infinity, oh, that must be wrong. Because as we go to infinity, we should approach the horizontal asymptote of 1. So I'm not sure exactly what this graph looks like. I'd have to think more about that. But it looks like we come down through, and then we are going to somehow approach a horizontal asymptote of 1. But there's a 0. Oh, the 0 is at negative 3. That's why. Fransky. So 0 is at negative 3. There's no 0 here. We approach a horizontal asymptote of 1. So it's going to come down through the hole and then approach the asymptote like that. So we wouldn't have this guy at the bottom. And that's definitely not a 0. And then over here probably will look like this. There we go. So we have that hole right there. But as the x values approach 1, the y values are getting really close to 2. Because we cancel that out, we just have a hole there. Now we get a conjugate 1. So if we plug in 0, let's see what we get. We get 1 minus the square root of 1 plus 0, which is the square root of 1. And then at the bottom we have 0. So this is 1 minus 1 over 0, which is 0 over 0. So we get that 0 over 0. We can't factor this, though. So let's try multiplying by the conjugate. So the conjugate, remember, we talk a lot about complex conjugates. In this case, we're starting with 1 minus root 1 plus x. So I'm going to multiply by 1 plus root 1 plus x on the top. And if I do it on the top, I got to do it on the bottom. So on the top, we're going to have to FOIL. 1 times 1 is 1. 1 times root 1 plus x is positive root 1 plus x. 1 times negative root 1 plus x is minus root 1 plus x, and that's the point of multiplying by the conjugate. They just cancel. Then negative root 1 plus x times positive root 1 plus x, when you multiply a square root by itself, the root just goes away, but it'll still be negative. So it'll be negative 1 plus x, and that is divided by, I'm just going to leave this factored, x times 1 plus square root of 1 plus x, because I think that's going to make my life a little easier. So on the top, let's look at what we have. The 1 minus 1 will cancel. So I have a negative x on top. On the bottom, I have x times 1 plus root 1 plus x. Hey, check it out. An x cancels. There we go. So that is negative 1 over 1 plus root 1 plus x. And if we evaluate that at x equals 0, so we're going to evaluate that at x equals 0. This is a little bit of calculus notation. We're evaluating it at x equals 0. That would be negative 1 over 1 plus root 1, which is negative 1/2. Oof. So the root one's a little bit tricky. Got to multiply by a conjugate. Not the most fun, but it doesn't kill you. It's not the end of the world. Okay, so we multiply by the conjugate, and then we just plug it in after we end up canceling that x, and we get negative 1/2 for that limit. All right, so your homework is to finish the white packet. So you're doing the rest of the limit problems. Shouldn't be too bad. I think you shouldn't have too much trouble with that. Just look through these examples again if you need some hints. It starts off with some infinity ones. Just don't forget, you do the degree of the top, the degree of the bottom, and you see which one is bigger. If it's bigger on top, infinity, bigger on the bottom, 0. Same, you look at the leading coefficients. So I'll be checking your homework tomorrow, page 749, which I was assigned yesterday, and then also the entire white packet. The sigma stuff, I know some people have been struggling with that a little bit. I've been getting some emails. We can talk more about that tomorrow, but if you look at the answers online and you struggle through it a little bit, I think you'll be able to figure it out. So do take a look at that, try it, give it your best shot, and we'll talk about it tomorrow if you still have questions. I love you guys. That's why I'm here. Have a great day.